Okay, so now we're going to get to the network layer, and this is quite a slog because there's a lot in the network layer when it comes to cloud, and there's a lot to understand at this layer. It's where most of the magic happens. It's a very tiny, narrow waist, but there's a lot going on in that layer, as it turns out. So you start with, it's a very simple thing that the network layer is intending to do: send a datagram from one host to another. And typically you would have the network layer on every single connected device on the internet. Some of the functions that you want a network layer to implement are whether or not it supports connections, such as the phone network, whether or not you have specific delivery semantics, and we'll get to that in a bit, whether or not you implement security at the network layer, demultiplexing to the upper layer protocol like TCP or UDP, doing the routing, doing the addressing. How do I address nodes on that network? There are many historical examples, and in fact, my undergraduate course in networking, I learned this, the OSI model that nobody uses anymore. So I took a whole semester, 15 weeks of completely useless information. Hopefully, with the internet, hopefully this 1 week of IP will last you many decades. I don't see IP being replaced ever. So hopefully this will be useful to you a decade from now. This is what the internet network layer looks like at a high level. You have this, the protocol itself is the header format of the datagrams that are being sent from one machine to the other. So this is the packet protocol, and it has in the protocol addressing conventions for saying source and destination addresses. It has the format of the datagram, so like the datagram length, for example, is specified in there. And then there's handling conventions of what does it mean to process a protocol packet, an IP, a network packet. The other part, so this is considered the data plane, the forwarding plane. The other part is the control plane. How do I actually get the routing to work? So I have a routing protocol that says I have all of these different destinations. How do I calculate a route from source to destination given a packet? So that's the complexity. So we have routing protocols doing some kind of routing algorithm, and they generate on each node a forwarding table. And the forwarding table says for this particular packet on this particular router, what is the next hop? It's a simple local forwarding table that a routing protocol, a global routing protocol, is going to be able to calculate a local forwarding table that when followed from hop to hop will get a packet from the source to the destination. So that's the second part. And then there's a control messaging protocol, which is at the very end for stuff like ping. So when you do a ping in that ARP lab, that's basically a control message protocol, which is a separate thing than what you would normally send over IP. So that is the picture. We're going to first go to just the IP protocol and talk a lot about that. This is the header. And a lot of the header is no longer relevant to us. So for example, this we're going to ignore. If you take the 594 class, you'll probably learn about what that stuff does. We don't care about it in this class. The things we care about the version number, because now there are multiple versions of IP that are floating around. We care about this thing, time to live, and this is part of ICMP, the control protocol stuff that we'll get to later. The upper layer, which says, I am in the network layer, where do I send this in the transport layer? So it could be TCP or UDP. That field is the field that specifies that. And then the source and the destination. And so this is a datagram format, and then the payload follows all of that. So as part of this, we talked about the things that a network layer can provide. The first thing is connection setup. And we already talked about with the hourglass design, we didn't really want full-fledged connection handling in the network layer. So all you're getting is datagram service. You're not having any sort of connection state in a router. And that was the innovation of IP. It's like, I'm not keeping track of connections. It's simply datagram service. And if you need a connection abstraction from source to destination, you're going to have to build that at the end hosts, right? Like, you do need a session. Like, if you're streaming from YouTube, like, you need the connection abstraction. So you need some end host process to be able to pretend like you actually have a long-lived connection with the server. It's not done inside of the routers. The routers are just forwarding packets, and that's all they do. They have no sense of connections that you might have to Netflix or YouTube. So compare this to the phone network. Yeah, you don't have anywhere in the routers where there's people plugging in stuff, and you have hard state in there. IP delivery semantics. There are no reliability guarantees in the network layer. Packets can be lost. There are no ordering guarantees. You can send 2 packets to Google and it could get them in reverse order. It could take different paths. There's no guarantee of any kind of delivery, order, or reliability. When you send a packet to a broadcast address, the broadcast address is not forwarded. So there's no broadcasting on the internet, which is good because then anybody could take down anybody else. There is no multicast, even though it might save bandwidth. Everything is done as unicast connections over the internet. There is no network layer multicast. It's mostly unicast, but recently in IPv4 networks, we've supported what's known as anycast. And an anycast abstraction says, I want you to reach the very first machine that can provide me a service. So for example, DNS is a perfect anycast service. It's like, I don't care which DNS server I get. Well, actually I do, but some people might not. It's just like, here's a DNS request. Whoever can service that, send me the result. And that, in fact, so this is done with protocol hacks. And that, in fact, is what is happening with Cloudflare. Any of you use 1.1.1.1? That is a anycasted IPv4 address that exists everywhere in the planet. Everywhere where Cloudflare has a presence, they will advertise 1.1.1.1 to whatever local presence they have. And you can do a trace route for 1.1.1.1 here, and it turns out their presence is in OHSU, just down the road. I think I'll do this, I might do this later on in the DNS lab where you can see where it shows up. You could go across the country, do a trace route at 1.1.1.1, and it's like, oh, lo and behold, it's just down the block from me. So there's a case where that IP address exists in multiple places. That's considered an anycast. And so if you do this, so this got launched last year. If you go to this DNSperformance.com, when they finally turned this thing on, they were the top performing DNS resolver. And they're like Google and, what is it, the the Route 53, Amazon, all of the other ones are like below it. Because the Google one is actually hosted in the DALs, I think. So it's much faster to get to the one in OHSU than to go to the DALs. So you'll see 1.1.1 is the top performing DNS server that's out there now. And that's done with an anycast. That's just an aside. So security, there's very weak support for integrity. There's actually, I glossed over this, but there's actually a checksum. And this checksum treats this whole thing as a bunch of integers, adds them all up, and then puts the result in there. And this allows you to detect whenever there's a bit that gets flipped in this packet, the checksum won't be valid, and then you're supposed to throw away that packet. But there's just it's weak integrity check is all that this thing does. It doesn't support authentication. It doesn't support secrecy. It doesn't support any of that stuff. It's all in the clear. Okay. The other thing that's interesting is that, there's a source field and a destination field in that packet. You can write whatever number you want as the source. It doesn't authenticate the source address at all. So this is what a spoofing attack is all about, where you will write in someone else's IP address, send it, say I bomb Google with someone else's IP address, the response will go to the victim, whatever IP address that I have selected. So this is a problem. Trusting the source to actually be truthful about the IP address is a problem. Okay, so in order to address this, there's this thing called IPsec, IP security, and the idea is to retrofit the IP network layer with encryption and authentication. And this is good. But if you think about WPA, how WPA is just a one-hop encrypted connection, the same thing with IPsec endpoints. it encrypts the thing but in that IPsec tunnel, but on the other side, it's decrypted. So again, if you really want end-to-end secrecy, authentication, and integrity, you need an end-to-end protocol. So you would need TLS, which we'll get to in the transport layer. You need something at the endpoints. Okay. Okay, the next thing is demultiplexing to the upper layer. You have this protocol type field. There's a control messaging. So if you have 1 in that type field, it goes to ICMP. We'll talk about that at the very end. If it's 6 or 17, it'll either go to TCP and UDP. This is the vast majority of the packets that you'll see go by are TCP and UDP, because HTTP uses TCP. The DNS will use either UDP or TCP. HTTP3 is going to use UDP, actually. So there will be a lot of UDP coming down the pipe in a couple years. There is a set of headers or protocol types that are for tunneling. So in particular, you can take one network packet and tunnel it in another network packet. Like, so say I'll get to that later. This allows you to create virtual networks, and we'll give an application of this later in this lecture. The last set of protocol types are routing protocols. So you need to be able to pass routing information over the internet, and that's what the 88 and 89 are. These are interior gateway protocols. Okay. The big thing that IP needs to support is routing. On the internet, routing is done on a hop-by-hop basis. Every router on the internet will create its own forwarding table, and the forwarding table is just going to calculate what is the next interface to go on for a particular packet. So given a destination IP address, what's the next hop IP address is what the forwarding table is. Okay, so in order to do this, it will implement a routing protocol and an algorithm, and it's just a graph algorithm. So in CS430, you do graph algorithms. That's basically what it's doing. There are 2 kinds of graph algorithms that are typically used to calculate shortest path routes on the internet. There are the link state algorithms. So in a link state algorithm, you basically collect the entire topology and the link values of the entire topology. And so this is what would happen in A. A would get all the link values and get the link information of the entire topology. And then it would do Dijkstra's shortest path algorithm. And this is sort of an iterative algorithm for taking this global information and being able to calculate shortest paths to each of the destinations in that graph. Okay? And this is typically done on edge networks. So for example, Portland State does a Dijkstra-like algorithm within its routers. The last I checked. The other kind of algorithm is the distance vector algorithm, and this is a gossiping algorithm. Rather than broadcast global link state to all the nodes, a single node knows its link information and basically broadcasts it to its neighbors. Its neighbors will learn about that and broadcast it to its neighbors, and then over a number of rounds, you will converge on a routing table that you can use to forward packets. So this is a decentralized sort of information broadcasting algorithm. And this is typically done on the backbone. So on the large tier 1 networks, exchanging information with BGP, it's using a distance vector algorithm. So those are the 2 ways of doing this. If you are interested in this stuff, that's all I'm going to cover here. The details are in the networking class. Okay, what I really want to get to is the issues with routing in IP. So the first thing that happens, assuming that I've got a routing algorithm that I want to use to calculate routes, the first issue is scale. We have, this is actually old, we have more than 200 million devices on the internet. You cannot run that routing algorithm like Dijkstra's on 200 million hosts with way more links is massive. Just the storage costs in terms of if you were able to finally develop a forwarding table for all 2 million devices, the storage cost on a router is prohibitive. Like you can't buy hardware fast enough for a routing table that has 200 million in it. The computation is prohibitive for 200 million destinations. And then the bandwidth is prohibitive. You can't broadcast that many link states across the internet, for example. The second issue is autonomy. So network administrators that own a certain subset of the network, they want to be able to control all of the routing that goes in and out of their infrastructure. So you want them to have administrative autonomy, right? Like if you're Comcast and you're building your network out, you don't want to have to deal with the AT&T next door also doing stuff. So you want to be able to have a way to isolate your stuff from everyone else's. So for example, any of the route changes that we make need to be hidden from everyone outside of Portland State. You don't want a route change locally here to disrupt connectivity somewhere else in the network. So those are the two things that you want. And because of this, you end up, this motivates what we call the internet routing hierarchy. And so the key observation is two things. You need less information with increasing distance to the destination. And this will then allow you to save the table size, right? Like rather than having information on every single host in the Portland State network, I could just say, you know what, I am Portland State 135.252, route stuff to my border. This is my border router. I just have one entry. And then all the internal stuff is hidden from everyone else outside. Okay. So we call this hierarchy, it's organized in what we call ASs. These are called autonomous systems. So within an AS, you have routers that can run the same routing protocol because it's all managed by the same autonomous unit. And this routing protocol that's done within the AS is called an intra-AS protocol or an interior gateway routing protocol. Those two protocols, the IGRP and the OSPF, those are interior routing protocols. And then in this AS, every node has global information within that network. So you can do the link flooding, you can do the broadcasting within that smaller AS. And then each node has routes to get to any node that's outside of the area. I don't care about anything else. Like I don't need, so if I'm going to Google from Portland State, the only thing I need on this thing is where is the border router that gets me out of Portland State. I don't actually need internal route information on Google's network. And so that's what this is also encapsulating. Okay? And this is done via a very special router in your in your AS called a border router. And this is an animation. Well, I'll get to the animation. Wow. Wow, this animation is really, the slide animation is really crazy. I'm going to go to the next slide, I think. Okay, so this is what's going on. So before the internet routing hierarchy, this was treated as one flat network, and you were calculating these routes globally. So if you have three autonomous systems, you have A, say A is Portland State, B is Lewis and Clark. We have a guest from Lewis and Clark, and then here's Portland Community College. This is what would happen. Addresses in B would be combined into a single route, and this route would be this border gateway router. And so what you can then do is instead of pointing to individual hosts inside of B, you can hide the topology of B behind this single route B.A. Similarly, for C, you can take C and the border router for C, and then that will hide all of the hosts within C. So you don't need information on C, that B doesn't need the specific information on C. And then the same thing with A. A has two border routers, so rather than having 4 entries in the route table, you would have 2 entries in the route table, and the topology on the inside would be hidden from the external. So that's basically how the routing hierarchy on the internet works, and that's how we get scale, right? That's how we can route to 4 billion hosts, is that we can do this kind of stuff to do the aggregation. Okay. So the key thing is that once you have this, you have another topology on top of the real topology. That treats this thing as like a virtual network, right? You have like this on the upper tier, you have another topology here that you can then run another routing protocol on. And the routing protocol you would run at this layer is called an inter-gateway routing protocol, which is what I had on the previous slide. But you would run a different protocol to get the routes in between A, B, and C together. Okay. So the routing can now be done between aggregates, and that's much more scalable. It reduces the number of routes. Okay, so at the top of this hierarchy are what we call Tier 1 ISPs, and these are the names of the world that you would recognize. These folks are running Tier 1 networks where they have presences in every part of the globe. So that's what we consider Tier 1. It has national and international coverage. And then in order to route from a Verizon customer to a CenturyLink customer, at different major metropolitan cities, they will what's known as peer with each other. So if Google, well, Google is on there, so I've used Verizon and CenturyLink. If there's a Verizon customer talking to a CenturyLink customer in Portland, then there will be a peering point where Verizon will hand off that packet to CenturyLink. Okay. One of the things with ISPs is that every ISP has a unique AS number. And these AS numbers and the IP addresses that they've been assigned, they're all well known. So if you're getting bombed by some IP address, you can look up that IP address to see where it's coming from and do some forensic analysis of, okay, this thing is from Saudi Arabia, or this thing is from Britain, or this thing is from South America. You can actually figure out where the thing is coming from. And when you are doing forensic analysis for sort of incident responses and security, this is where you would start to trace information about the source. And so that's what this AS number is. So it's important for that kind of attribution. Yes? You can fake the source of a network packet, but then to actually fake an end-to-end connection, the responses will end up going to a legitimate. So you can fake a connection attempt, but the response is actually going to go to the legitimate person, and then that person is going to say, that didn't come from me, I'm going to reset the connection. But it's hard to actually do a full-fledged connection without owning the IP address. And then to do that, you would actually have to compromise the machine. So it's more likely, like if the Russians didn't want to know that they attacked us, they would find some other source. They would compromise a machine in another country and attack us from there. So forensic analysis doesn't always, it's not, the be-all, end-all isn't the IP address, but it's just one part of the thing that would allow you to do the attribution to a particular country. Yeah. A lot of times they're looking at the software that the person is using, because typically nation states have well-developed attack kits, and so when you see the thing being used, then you would say, okay, that's probably Israeli, or that's Russian, or that might be Chinese. Yep. But that's more of a security thing, not a cloud thing. Well, it might be a cloud thing actually, because a lot of people, the cloud's getting attacked, so it will be a cloud thing. Okay. So this is a map of CenturyLinks. This is like from 10 or 15 years ago, but it probably looks the same. All the different points of presence that this Tier 1 ISP has. And it needs these presences to serve its customers, because its customers want a fast connection to anybody on the internet. And so people on the internet are everywhere, so you need a peering point in every single geographic location that has enough people in it. And so this is what you'll see in a Tier 1 network, nationwide or international coverage, peering points in every single one. Okay, so you can see that, hey, Portland made the list, right? There we are. We're like worthy of having a peering point for CenturyLink. And sure enough, we do. So here's a question, and don't look ahead if you have the slides, which building do most of Portland's packets go through? Anybody know? Does anybody know where this is? Do you know what this is going to be? This is going to be a big old hotel. This is what is it, a Westin? A Ritz. I think it's a Ritz. This is where the new Ritz hotel is. This is the Pittock block. This is actually where more than 80% of all packets in Portland will end up right there. So if you were really a miscreant and you wanted to turn off everyone's internet, maybe you're a mad parent that your kid is addicted to the internet, you would attack that thing, this thing, right? Like the PIDIC block is where all of our network traffic goes to. So I bring this up because this is sort of a fun thing. This is named, so this is the local thing. This is named after that PIDIC, the same PIDIC that mansion. So basically the story is that he used to live on that block, and then he was building that mansion in the 1915s, like 1915, 1960 range, 16 range, and he's like, okay, I'm gonna move. So he moved to that mansion, which is beautiful if you've ever visited it. It's a beautiful mansion. He's like, I'm gonna move there, but I wanna take my house downtown and I wanna turn it into something really cool. And at the time, the really cool thing to put there was an electrical substation. So if you've never had electricity before, electricity is pretty cool. So that is what they built in that PIDIC block. And so you can see when you build an electrical substation, you got a lot of conduit and a lot of space. And so when the internet boom happened, they're like, hey, we got conduit to all sorts of places in Portland. It's already built, and we have this enormous sub-basement that used to house an electrical substation. Let's put an internet exchange point in there. And that's what they did in the early 2000s. And so you can see the remnants of the sub-basement. The sub-basement used to house they say it used to house the Oregonian printing presses. So you can see old newspapers plastered on the wall. And this, I highly recommend visiting this link. This guy has gone down through the basement and taken all sorts of really cool pictures of what that sub-basement looks like. And there's some stories about the whole thing at these two links. So the Northwest Access Exchange is located on the PIDIC block for exactly this reason. Centrally located, has conduit everywhere, so almost all of the fiber was routed to the PIDIC block. And this is where all of the ISPs, the tier 1 ISPs, are exchanging traffic with each other in Portland, is down in the PIDIC block. And you can, when we do the trace routes from different places to here, you can see in the names, you can see the PIDIC block show up on several of those. You can actually you can click on the members, and you can actually see the interfaces that they own on the Northwest Access Exchange. I did a screenshot just before I got here. You can see that Google, with its AS number 15169, has a connection in the PIDIC block on that IP address. Portland Community College has one. Portland State, Puppet's got a presence there. I didn't check for Lewis and Clark, but probably, right? So all of them have presences in the PIDIC block. Okay, so this is what it kind of looks like. You have a routing hierarchy. You have tier 1 ISPs. From the tier 1, you might have a bunch of tier 2 ISPs. Like if you go down that list of members, you'll see smaller ISPs that are there, and then so on. So you have this hierarchy of ISPs. And as it turns out, when your packet gets sent from the source to the destination, you're going through a whole bunch of different administrative zones. And that's allowable using the way that the hierarchy has been implemented. Okay, so between the ASs, I mentioned that you have this topology that's actually on top of the physical connections. It's like a virtual topology. And we're going to talk about virtual topologies because that is basically everywhere in the cloud, a virtual network. So you have a virtual network where the peering points are all nodes in a network. And in order for them to route properly between ASs, they have to run a routing protocol. And that routing protocol is called BGP. So the inter-AS routing is done with BGP, and it uses distance vector to basically gossip routes across the internet. So it treats each AS as a node in a graph, and then each AS has a route that will aggregate all of the destinations in its AS within it to everybody else on the network, so that you can get a smaller number of routes in a routing table. So there could be several thousand routes in a routing table rather than hundreds of millions in a routing table. And that's the magic. That allows you to shrink the routing tables enough to basically scale the internet for all of these hosts. Okay. One of the things that I should note is that all the BGP messages are exchanged using TCP, which is one of the transport layer protocols. This simplifies BGP, but TCP is kind of a house of cards. TCP and IP in particular have no support for authentication. So we talked about spoofing attacks already. BGP has a TCP spoofing attack that allows someone remotely to reset a router-to-router connection by guessing sequence numbers and guessing sources and destinations. You can cause a lot of disruption by sending packets to reset routing connections on the internet, and people have done that. And so it has an issue with spoofing attack. It also has an issue with bogus route advertisements. I can pretend at home that I own Portland State's IP addresses. I'm like, 131.252, that's all me. And route all the packets to me, and there's no authentication. Like, anybody can announce that they own these addresses, unfortunately. And you're just like, how is that possible? How are we relying on the internet working with that kind of thing, right? We'll get to that. We'll get to this later. Why it's happening and what they are or aren't doing about it, actually. Okay. The next thing I want to cover in terms of IP is the way it does addressing. So, and I'm specifically talking about IPv4. So most of what you're familiar with is IPv4. It has a structure that has 4 numbers, and these are 4 octets. They're basically bytes. They represent bytes from 0 to 255. And so in order to make it easier to write out, because you don't want to be writing out binary, so you have 4 decimals, and each of the decimals goes from 0 to 255. And so 131, 252, 220.1, this is 131 in binary, this is 252, this is 220, and there's 1. So 4 individual bytes, 4 decimals from 0 to 255. So if you remembered CS430 very well, what's the total number of addresses that we have approximately with 32 bits? Who's got it in their head? 4 billion, about 4 billion addresses. When we assign an IP address, we assign it to an interface, not a machine. And this is a nuance, because if you have a machine that's got a Bluetooth interface, a 5G interface, a Wi-Fi interface, an Ethernet interface, you got lots of interfaces. Each one of those interfaces would get an IP address if you wanted to make them routable on the internet. So the IP address is actually bound to the interface, and not the actual machine. The router, for example, always has to have multiple interfaces, and so they would always have multiple IP addresses to support the routing from one interface to the other. The host can have multiple interfaces, both real and virtual. So for example, if you have a virtual machine on your computer and you have networking going to the host, but you also want networking to go to the guest operating system, you can actually set the guest to be in what they call bridging mode, to have an actual full-fledged presence on the network. And the way VirtualBox does that is to bring up a virtual network interface to allow it to respond to 2 different IP addresses. And so you can then get on a single machine 2 IP addresses, one for your virtual machine, one for the host. So, okay. So the key thing with IP addressing is that it supports aggregation. So we just talked about the importance of being able to aggregate routes into one prefix that represents a whole bunch of machines. The way this is done is to take an IP address, and if you want to specify blocks of IP addresses, for example, all of the IP addresses in a particular subnetwork, like here, then the way you would specify that is to split the address into 2 parts. You'll have a network part, which is the high order bits of the address, and then the low order bits are the host part. And so what is a network? The network is basically everything that's directly connected to each other. And so each interface on this network would share the same network part. And then the host part would be the only part that would differ. So in this case, we have 3 networks, and each one of them has a network prefix. So in this case, the prefix is 223.1.1. That's 1.2. This is 1.3. And then the low order part is the last byte in this figure. You could draw this differently if you had a different demarcation, but this is for this figure. It's 3 networks done in that fashion. Okay. So the IP addressing uses what's called CIDR to do the aggregation. This is the acronym is Classless Interdomain Routing. So the network part in CIDR can be arbitrarily sized. You can move that network boundary up and down the address to aggregate in different levels. So the more you shift that boundary to the left, the bigger your network gets, the bigger the aggregate is. The more you shift that over to the right, towards the lower parts, then the smaller your network is. Okay? And this is done throughout the routing infrastructure. So at Portland State, all of our routes are like /24s or /25s. The network part is all the way towards the end. When you get up to the tier 1, you'll see that a lot of the routes are all the way to /16. They're sort of towards the middle, where they've aggregated large blocks of. In fact, Portland State is a /16. So that's what we aggregate all of our /24s and /23s into a single /16, 131.252. That's what we advertise in our Northwest Access Exchange. We advertise one route that says 131.252. Right here in the Piddock block is where I am, and that's our route entry to the rest of the internet. Okay, so the mechanism for doing this, for aggregating adjacent addresses together into a larger prefix, that's called supernetting. For taking a big block and splitting all the adjacent addresses apart, that's called subnetting. Okay. So a single integer in CIDR will specify the demarcation between the network and the host parts of a prefix. So you will typically see this notation, the network prefix, and this will be the full IP address, the 32-bit IP address, and then the bits in the prefix that specify the network. So for example, you might see something like this, 223.16.0, and the /23 says of this IP address, only the first 23 bits are used to specify the network. And then everything else is the host part. Okay, so this basically says you use the least significant bit here and then the last nibble as the host part. Because this basically gives you 9 bits of host. So that would be you steal a bit from the other, the second number. So this is what it looks like. So 200, 23, 16, and 0. And you count out 23 bits, and this is the network prefix, and then the host part is everything in the black. With that. So this is important because this actually maps to a range of IP addresses. So if you're taking, and this happens a lot, when you're taking your enterprise network and you're shifting it into the cloud, one of the things that you're going to have to do is set up networks and subnets in the cloud. The notation for specifying all that is in CIDR prefixes. You say, hey, I have 25 machines on this particular subnet, give me a /28. No, the /27 to host that subnetwork. And that's what it's referring to. It's referring to a range of IP addresses that all share the same physical network. And then Google will go and reconfigure things so that it implements that for you. Okay. So the host will then, if you give them this prefix, that means the host can range from all zeros here to all ones. Everything in between those all zeros and all ones are are IP addresses that belong to this prefix. So in this case, if you do the translation, this means that this prefix specifies IP addresses from 223.16.0 to 223, this is 17, and this is 255. So every address in between these two will fall under this prefix. Does that make sense? Okay. This is getting the binary number. And we don't cover the binary number system after 201 very much, do we? So this will hopefully refresh that, which I think is probably pretty important. When you get to networking, you need all that stuff. Okay, so subnetting walkthrough. So here's an exercise that I'll walk through. Take a large block and split it into smaller subnetworks. So the exercise here is I have this larger prefix, 131.252.0.0.22, and I want to split this into 4 equal subnetworks. So the way I would do this is I would take this prefix, I would write it all out, and then I will figure out where the 22 boundary is. And so here is 22 bits, and those last 10 bits are the host part. And so now I want to first figure out how many hosts are on this prefix. How many hosts belong in this prefix? If you know the power of 2, just yell it out. Otherwise, just give me the power of 2. 1024. So it's 2 to the 10th. There are 10 bits. So the number of combinations of bits is 2 to the 10th. So there's 1,024 hosts on this CIDR prefix. The second question is how many hosts will be on each subnetwork then? 256, because I want to put this into 4 equal subnetworks. And so the way I would then split this thing up into 4 is to take the next 2 significant bits, because you need 2 bits to specify 4 parts. I would take these 2 significant bits, and I would use those to split up the rest of the space. So that is what we'll do to do the subnetting. We will grab the next 2 bits, 00, 01, 10, and 11, and these are now 4 different CIDR prefixes that will evenly divvy up that address space. And if you then generate the CIDR prefix for each one of these, this is 131.252.0.0, but instead of 22 bits that are part of the network ID, you have 24 bits. So that's what this is. And then this is 131.252.1.0, and then 24 bits, and then so on. Does everyone see how we just subnetted that larger block? Okay. Here's another problem, and I'm going to have you do this with the person next to you. Why don't you solve this on your own and then compare your answer with your neighbor? And I'll give you a couple minutes to do this. Split the following network into 16 equal subnetworks. And the answer's not there, but I want us to generate this on the fly. Okay, so this is the way I would do it. You know that you need 16 equal subnetworks. So you need the next 4 bits. So in order to get 16 different parts, you need 4 bits to do that. So you take the next 4 bits and you say, okay, this is now 0000, 0001, 0010, all the way to 1111. And if you look at this one, this stays the same. This is 131, This is 131, 252, 128.0. But now, whoa, what did I do there? But now the prefix is over here. So that is 17, 18, 19, 20, 21. This is a /21 now, because I used the next 4 bits. This prefix is 128 plus 8, so this is 136. And then so on. So you're just at, this is, the next one is 144, all the way down, and you don't have to fill out the rest, but that's basically what you would get. 16 different subnets out of this single CIDR prefix. So as Portland State starts to divvy up IP addresses to smaller, like for example CS gets a small block, class gets another small block, they will subnet their allocation. They have a /16 at the top. They will start subnetting those to individual units on campus. And then we will be routing with these prefixes internally. So when we run our link state protocol to do the routing, we're going to throw around these things. And then we will have globally visible routes between each of the machines in PSU, but we will only have one route towards the internet. So the routing tables will still be quite small, and that's how we'll do the routing locally. Or yeah. Are there questions about what I just did? Okay. So the next thing is supernetting, and it's the reverse. So hopefully this is a little bit easier. Take small blocks and combine them to reduce the number of routes. So you're doing the opposite. Portland State has a whole bunch of routes. It needs to aggregate them into a larger CIDR prefix because it wants to advertise the larger prefix. So that is the opposite operation. So here, combine the following Class C subnetworks. So Class C refers to a /24. Combine these 2 subnetworks into one larger network. I'll actually walk through this. So the way you would do this is you would expand out the IP address in bits. You would demark the network part from the host part, and then you would take a look at the structure of the addresses. So this is what I'll do. I have the prefix, the 24 bits, and then I have this .* because the .* could be all zeros to all ones. So this is where the host part is, and the host part could be any of those. But if you look at this, if I want to combine this top one with this bottom one, if you can see, they share the same prefix up until this bit. But this bit could be either 0 or 1, and then have all of the other patterns beyond that. So in this case, if I could combine these 2 into a single prefix where this is a star, if you remember your regular expressions. So you could, and I have poorly highlighted this here, you could then in red make that the new host part, and that would specify all 512 patterns from all zeros to all ones. So this is what you would do for supernetting. You would take that and you would say, you know what, now this prefix that has, where's my cursor? I don't have a cursor. This prefix, which now has that last bit that can be part of the host and has the rest of the bits. This is the /23 that combines the 2 /24s together into one. Are there any questions about supernetting and how this works? Yeah.
So the star, does it mean that it can be only all zeros or only all ones, or is it any combination?
Any combination. Yeah, the star means it'll match everything. So yeah. Probably poor notation. I don't know. Yeah, we use star for regular expressions, but like networking, I just use star. I like mixing and matching my CS stuff. So yeah, that means like a regular expression star. So it's awful. I probably shouldn't, but alas. Okay, so There's another question is, can you combine, so here we combine 0.0/24 with 1.0/24. The question is, can you combine 1.0/24 with 2.0/24? Right? Can I combine any adjacent /24, any two adjacent /24s into a larger /23? And it turns out the answer is no. And the answer is no because if you write out the prefixes here, you get something that looks like this. You have something here that is 01 dot star, and the next one is 10 dot star. If you look at their /23, they don't match. They're not on a contiguous boundary that you can actually combine those two things. They actually belong to different prefixes in the /23. So this is a problem. So you're not able to just take any two /24s and combine them. They have to be aligned. This is similar to memory alignment in CS201. You can't just put two things adjacent to each other on the same cache line, right? Like you gotta align the addresses so that they're actually they can be contiguous in a cache line. Okay, so no, they don't share the same address prefix. Only ranges that are aligned properly, that can go from all zeros to all ones and share the same prefix, can be combined, is the take home for this. Okay, so here you can combine these two, which is what we did earlier. The 0.0/24 and the 1.0/24, those can be combined. And that's what we did before in the previous slide. We combined these two prefixes to get the /23. You can also combine the 2.0/24 with the next one, 3.0/24. And I'll show you this. This is the bit pattern for that. And you see in the first 23 bits, they do have the same prefix. And then the other two bits can be, the other bit can be either a 0 or a 1, and then any of the host parts will work. So this allows you to then aggregate these two subnets into 131.252.2/23, because this is going to be a 1, 0. Does that thing make sense? Okay, so then the next exercise is for you to take these 8 /24s and combine them into one-sider prefix. And I'll give you 5 minutes to do that. Well, not 5. Yeah. All right, 5 minutes. I'll give you 5. Okay, so what you'll end up with when you write out all these prefixes, this is the 0, this is the third octet, this is the 0, the 1, the 2, the 3, the 4, the 5, the 6, and the 7. And you can see that this specifies all the bit patterns in this column, right? So this is all the bit patterns that you can get for the last 3 bits. So you can combine all of this with the host part to create that one prefix. So this would make this a 131.252.0.0/21. Excellent. So yeah, this is what the answer is. Okay. And this is how you will see blocks of IP addresses in the cloud be referred to with their CIDR prefix. Actually, anywhere. If you're configuring routers, you'll be configuring stuff with CIDR prefixes. It's just the shorthand notation of specifying ranges of addresses. Okay. Okay, I would now want to talk about special IP addresses. Because you'll get to see a whole bunch of these special IP addresses, and you'll think that they are regular IP addresses, but then you'll try and use them, and they're totally not. So the first special address is the loopback address, and this is we call this the self-talk address. So if a machine likes talking to itself, it would actually put a lot of traffic on the loopback interface. So you can see with ifconfig that typically the loopback is given a IPv4 address of 127.0.0.1. This is not an IP address that goes out onto the network. It just goes back to the computer itself. Now there are some servers that will bring themselves up and they don't want external connections from anywhere else except for other programs on the same machine. What they'll do is they'll listen on the loopback interface and then, oops, sorry. They'll, in fact, hang on, make sure turn my ringer off. It'll make sure that only programs from the current machine are able to access it. Nobody else externally can do this. So there are some, so I'm teaching the blockchain class this quarter. There are some crypto wallets that will listen just on the loopback interface to allow other programs to access the wallet that are only on that computer, but let no one else from another machine access that wallet's REST API, or I think it's a REST API that it has. Everything's a REST API. So, so that's the loopback. And you can see there's an Internet IP version 6 as well. It listens on both of those. Okay. Another set of IP addresses are the private ones, and these addresses are not globally routable. You stick a packet with one of these addresses onto the internet, and it'll bounce, usually. So private IP addresses, there are 3 ranges of IP addresses that BGP will just drop. If you advertise you have a route to any of these things, it'll just drop all of that because it knows that those are special ones that are just used for internal networks. And in fact, Portland State uses the 10 prefix for a lot of its internal machines because we don't have, we have a /16, we have way more machines now at Portland State than can accommodate the /16. So it's like 65,000 machines is what a /16 has. We have more than that. Heck, for students, we have like 23,000. And then I'm using a lot of IP addresses in our range. So we're using way more than we can. So a lot of the machines now, for example, in the Linux lab, the particle machine, all those machines are using the 10 prefix. So you can't SSH into those things because they have a private IP address. You have to come into Portland State and then SSH into one of those particle machines. Similarly, and you'll also see this if you have a home router and you are trying to get an IP address for your laptop connecting to your home router. Typically, the home router is going to issue you private IP addresses. So that you can get an IP address without trying to claim a globally routable one, and then it'll do some other operation to make sure you can get onto the internet, which we'll talk about in a minute. Okay, so these are special ranges. Google, for your compute engine instances, when you bring up a compute engine, you will get an externally routable IP address that could be random, but you will always get assigned an internal IP address that always has the 10 prefix. So the internal IP address, that is the one you're going to try and use when you're doing stuff like Nmap. When you do an Nmap, when you get to the Nmap lab, if you want to avoid getting flagged for abuse, when you do your Nmap, make sure it goes to the private IP address range. And those IP addresses are confined to just your project. just your virtual network in your project. Okay. So you can see in the particle lab, if you do an NS lookup of catron.cs.pdx.edu, and this is in 8809, you can see that it's using a 10 prefix, so that when I have a machine that's outside of the Portland State Network and I try and SSH into it, it says it's not reachable because it's got this 10 prefix. Yeah. You have to tunnel to a machine on campus that has the routes for the 10 network on it. So as part of Portland State's routing infrastructure, we will actually have a routing infrastructure for the 10 network. And so you just have to tunnel into a machine here that's got that route, and then you can then hop over to Catron, which is what I think I'll show next. So now you have to go through a machine at Portland State that's got an externally routable IP address. So linux.cs.pdx.edu, if you look that one up, it's got a 131.252. So then you can SSH into that, and this machine knows all about the 10 network, the local private 10 network, and then from here, you can then SSH into Catron, and then this will be your, and actually this is logged in on the IPv6, but then you have globally routable, or you have routes that will give you the 10 network within Portland State. So, okay. All right. Okay, so all the Google Cloud internal interfaces use the private network. So here's a virtual machine. It's got the external IP address that's basically globally routable. You can actually hit this from Portland State. And then this is the internal IP address, not globally routable. So this is the one that you would want to nmap and not that, that one. Okay, so I mentioned that CIDR was being used to both aggregate and split up ranges of network addresses. I just wanted to finish off CIDR with a picture of how this works. So here I have ISPX and ISPW. ISPW is maybe your tier 1 provider, and it says, you know what, you are another big ISP, I'm going to give you this big subrange. So here is a .16.0/20, and any address that comes to ISPW with this prefix that matches will go to ISPX. Now ISPX is routing, has taken this /20 and has split it up. So in this case, it has split it up into 4 different kinds of chunks. It takes half of this range and it gives it to this large company. It takes a quarter of it and goes to the medium company. It takes an eighth of it, goes to the small company, and a 16th of it goes to this tiny company. And so within ISPX, ISPX would hold, so this half would be a /21. So from the /20, you can allocate a /21. So this is a single route. So ISPX would have these 4 routes in it. It would have the single route. Where's my pointer? It would have the single route to the large company, and then it would take a quarter of the IP addresses in this, the medium company, and it would generate a single CIDR prefix for that one, and likewise for the small and the tiny. And this routing table would have 4 routes rather than a single route, because as you get closer to the destination, you need more information. So this is where the subnetting happens at ISPX, and then this allows you to route effectively right when you need it, right? You get the information in a routing table right when you need that information. Does this make sense? And it still has a 16th that's unused over here, which doesn't, that's not part of the routing table. It would just get sent to the default route. Okay. Okay, one of the interesting things on the internet is that you want to be fault tolerant. So Portland State doesn't just have one interface at the PIDIC block. We actually have a peering point to other places, right? Because if someone does blow up the PIDIC block, we need to submit our homework through some other way. So there are multiple peering points. And so you get to this case so for example, this small company says, I don't want to rely on ISP-X. I want to be able to, when ISP-X has a power outage, I want to be able to take my network traffic and route it to ISP-Y. And then ISP-Y will also advertise that it has a route to this range of IP addresses available to it. When ISP-W sees that this block can be reachable from X and Y, how does it decide where to send packets to? The routes overlap, right? I have this larger prefix, this /20, that is a sub-block of this /20 is being advertised through this backup ISP as a /24. So when overlapping routes occur on the internet, the rule that is followed is that you always follow the more specific route. So if you match two routes, so if I have a packet to ISP to this person, and I'm in ISPW and I have these two routes, and I match the one below it, this route is the more specific route. It has more bits that match. So then I would, by default, forward onto interface 2. And then it would go this way. So that is just the convention of routing. You have a question or no? All right. So the algorithm that all the routers perform is this longest prefix matching algorithm. So you have a route table up here, and it says that this prefix, and I only show the bits that matter in the prefix. Yes? So if I have a destination IP address that says, here's my destination, the forwarding table has a bunch of prefixes and a bunch of next hops. And so I'll take my IP address and I'll say, hey, here are the routes. Which one matches my destination IP address? And then if it matches this pattern, this really long one, I can go on interface 1. So the routing protocol generates the forwarding table. This is the forwarding table. And the forwarding table takes a bunch of prefixes and says, if you match any of these, go on this interface. Now, if you match on multiple ones, so for example, this interface, or this route and this route overlap, right? I can have a packet that matches both of those. In fact, this packet right here, if I do this, and the rest of this is all zeros, so if my destination is this with all zeros, it matches this prefix and this prefix. They're both the same. They overlap. So the algorithm is, if you match multiple prefixes, do the longer one. So if I do have that address, I will go on link interface 1. Okay? So I will walk through this. So here are some packets. So the routing table ends here. And these are just, these 4 are just packets that I get, the destination IP address of the packet. So if you look, where does this one go to? So this goes over interface 1 because it matches both of these, but obviously this is a longer match. What about this one? This one matches this one, the first one, 1, 0. So this is, sorry about the alignment, 0, 0, 1, 0. So this is 0, 0, wait, 0, 0, 0, 1, 0. So 0, 0, 0, 1, 0, so it matches that one. So link interface 0. It's a bit of an eye chart here. So 0, 0, 0, 1, 1, 1, 1. So this matches this one. 0, 0, 0, 1, 1, and then 1, 1. So that matches interface 2. And then this one is 0, 0, 0, 0, 1. And you see 0, 0, 0, it matches the default, right? Doesn't match any of those other 3, so then the default route is to route on interface 3. This is what your router is doing billions of times a second, doing a longest prefix match operation and forwarding it on to the next interface. Okay? Okay, so what if, I'm getting back to something I had mentioned earlier, what if YouTube, with its network traffic going through X, so it advertises, it's got more than a /24, but let's just say this is early YouTube. It's got a /24, and it advertises through Google is the ISPX here, that it has this traffic, and then has this, ISPX has this route table. What happens if it also has a prefix 30.0/24, and some other ISP over here says, I own that prefix, send the traffic to me, and I'm going to insert this route into the routing table. What happens at ISPW when this happens? Where does the traffic go to? The first one or the second one? The second one. So it goes to the evil ISP. So this, in fact, is what happened in 2008. So Pakistan didn't like what was being hosted on YouTube, says the way to solve this is to advertise to my people that I own YouTube, the government. And of course, because we're all connected on the internet, that route advertisement, because it was more specific than what Google was advertising, that ended up being adopted by all of the different ISPs, and YouTube went out for like 18 hours. I don't know if you could remember this, if you were YouTubing back then. I was YouTubing back then, so I remember it. That's why this is on the slide. But yeah, they took all of YouTube's traffic, and then we had to do something else for entertainment for that day.
How did they fix that?
They had to go, so there's this group called NANOG, which is the North American Network Operators Group, that tries to operationalize things to do when stuff like that happens. And so they have to coordinate a response to start removing and blacklisting that particular advertisement. But it's hard to blacklist all the dumb stuff that people can do, unfortunately. You can't say, don't do this, don't do this, don't do this, and then someone will find a new way to mess things up. So you would like to fix it at a more fundamental level, and the more fundamental level is to use some kind of public key infrastructure and signing keys, and they've been working on that for ages, and it's still not, there's a whole bunch of technical problems that make it hard to do that. And you might think, oh, that happened over 10 years ago, that would never happen now, but lo and behold, Google did this to the entire country of Japan in 2017. My favorite part of this is that somebody in Google fat-thumbed a border gateway protocol advertisement, and that's what brought Japan down. So they just messed up the prefix, and then all of Japan's network traffic came to Google, is effectively what happened. People, like nation states, can do this too. And so people are like, was this a coincidence that Google, Facebook, and Microsoft were somehow temporarily routed through Russia temporarily? This happened 2 years ago. There was another one that's more recent. There are cases of this happening when you want to hijack someone's crypto wallet. If you have a high-value target, then you can route the traffic to whichever exchange that person's using to yourself, get his private key, and then just steal all of his money. So that actually happened as well. I don't have a link to it in the slides, but I have it somewhere else that I can send out to the channel. And then this one, Iran. They think that this went through Iran, and at the time, all of its dissidents were using a Telegram, which is end-to-end encrypted. And so they were trying to make sure that the use of that was disabled. So the way they tried to disable it is to hijack the Telegram traffic. If you know that all that traffic goes to a specific destination, you black hole it, you sinkhole it, and then you see. But the problem is that when you try and sinkhole that route, you're sinkholing it for everybody because of the way BGP works. So every couple of years, they say, no, we're really going to solve this problem this time. And the thing with Russia happened, and then they were like, okay, we're going to really solve it this time. And we haven't yet. So this is, work in progress. Okay. So one of the things on the Linux host that you can do to look at your own route table is to do this thing called netstat-rn, which is part of your ARP lab. When you do a netstat-rn, you basically dump the routing table like we just showed you earlier. And the way to parse this routing table The terminology going across the columns that you care about are the destination route. So this is the network prefix on the left. The gateway is basically similar to the interface. What is the next hop? If I match this route, then the next hop is this. The gen mask is the CIDR prefix. It's the netmax, the integer. It's just encoded differently. So here is a /24. It's just specifying the bit position where the network ID ends in a different format. So it's just writing it all out. So here is a /0. That means everything matches. This is a /24, which means that the first 24 bits need to match. And this is a /16, where the first 16 bits need to match. So that's what the gen mask is doing. It's giving you the bits in the prefix. The other thing is the iFace. So this is the interface that you would then forward the packet to if you have a route that matches your packet. And so if you look at this, there's two, this is the real Ethernet card on this machine. So two Ethernet interfaces, and you see this Docker 0 interface. This is a virtual interface for you to communicate with any container that you're running on that machine. So when you run a Docker container, which you will in about 3 or 4 weeks, when you bring up Docker on a machine, it needs to have a network, right? Like, it doesn't make sense to have a Docker container that can't communicate with the network. It will communicate over this virtual interface called Docker 0. And it needs a route. So when you bring up a Docker container, in this case, the Docker container is going to have a network interface on 172.17.0.0. And that's part of the private IP address range that we saw earlier. And so that's how the networking is done on the host to take traffic to and from the container and to and from other parts of the internet with one routing table. So the way you parse this routing table is that the first one says that all destinations, this is your default route. When you say this bit pattern with /0, that everything matches that. And it says the default route will send a packet to this address. And it turns out this is our default router on our subnet, this .250. So this is our connection to the internet. So route to this gateway, and that gateway can be reached from ETH0. So that sends it out to my Ethernet card, basically. Any destinations matching 131.252.220/24, well, that matches machines that are on my subnet. These are the machines that are directly connected to me, and I don't need to send that to the gateway. I can just directly ARP for that IP address because I know we're all connected on the same subnet. So this allows me to know all the things that are directly connected to me and send a packet directly to them rather than going through the gateway. So all of those packets will go out ETH0 also because they're also connected to me. And then finally, destinations matching this private range, they'll go over the Docker 0 interface. And hopefully something is listening on the other side that will take that packet in. And usually this is. So this is how Docker containers are networked by default. Okay. Wow, I'm going to use everything again. How far? All right, I'm going to stop at this. One of the things that CIDR was designed to do was to address IP address depletion. So right at the beginning, when we had 4 billion addresses, we were like, sweet, we're never going to run out of these. 4 billion, that's way too many for the number of machines. So you know what? I'll give you 65,000 IP addresses. I'll give you 65,000. It's like a free-for-all. I'll give you 100,000. We got so many, I'm just giving them away. Well, as it turns out, you give them away these large blocks of IP addresses, and nobody has a network big enough to actually fill it. And so we had this issue of IP address depletion that CIDR helped, because when you can subnet these large blocks, then you can start divvying up the subnets to smaller organizations. And so, but still, even with CIDR, we're really running out of IP addresses. And as it turns out, AARON, which is the large organization that sort of assigns IP addresses, they gave out their last North American prefix in 2015. And then they gave away their last prefix entirely in 2018. So now we have no more IPv4 addresses to give out. And so in order to address this problem, we have this thing called network address translation. And this is what I'll start with next class. That is basically in almost all network deployments that you now have to navigate around in order to operate. So I'll end here.